Today, I'm going to relate my team's experiences in collaboratively developing what we call first-tier cyber infrastructure for geochronologists. It's a collaboration among software engineers and earth scientists. In our case, first tier refers to the automation of workflows of geochronologists analyzing rock samples using mass spectrometers and eventually archiving digital records of their work in public repositories, where these and thousands of other results can be used by second-tier cyber infrastructure. I'll present my background, make a plug for the EarthCube demonstration governance, and then I'll describe the origins and evolution of our unique collaborative development of first-tier cyber infrastructure. It bridges what we call a software chasm between earth scientists, in this case represented by EarthTime, and software engineers represented by CERTLS, the Cyber Infrastructure Research and Development Lab for the Earth Sciences at the College of Charleston. I'll conclude with some thoughts and ask for your questions. I'm an assistant professor in the Department of Computer Science at the College of Charleston. My teaching is primarily in software design, engineering, and testing. The college is a primarily undergraduate institution, although we have a master's program in computer science. And my research is centered around this CERTLS, which is at certls.org if you're online and want to look, and I'm the principal investigator there. I'm also a collaborator with EarthTime, more about that in a moment, and I've worked with the EarthCube project for a number of years, and I'm a member of the test enterprise governance effort, which is just coming to an end, and I'm also PI of the Special Interest Group for Software Engineering Communities of Practice, part of EarthCube. I want to first, though, show this picture of a new bridge, now it's from 2005 in Charleston. It is the longest cable stay bridge in North America, and it's rather stunning piece of work. You can see the bridge it replaces, which is now gone in the distance. It's a, or next to it, it's a truss bridge. But I'm using this as a metaphor for bridging the software chasm that I'll describe shortly. And plus, it's just a beautiful bridge. And I'm inviting you to Charleston whenever you can come. So, EarthCube, we're having an EarthCube webinar today, and I wanted to bring your attention to the fact that EarthCube is moving into its next phase, that of demonstration governance. And this is a really important phase. This is where the community takes control, right? And so the notion here is that people need to volunteer to become part of demonstration governance and to actually try to test the effectiveness of our proposed charter and then work to adjust it to meet the real needs of the community. The charter was proposed this summer at an all-hands meeting in Washington. So you can help by volunteering to participate in one of these four teams or committees: the engagement team, the liaison team, technology and architecture committee, and the science committee. EarthCube is currently open to anyone, no fees, no barriers. Everyone can belong and everyone can vote. And you can find out more about these teams at this website here, which is part of, we're on this website now, I guess, with this webinar, but under the demonstration governance section, there's all kinds of information about these teams and how you can join. I encourage you to do so. Or you can email one of the administrators here, Anna Katz at the Arizona Geological Survey. So the motivation for this collaboration that I'm talking about today came from discussions in 2006 with geochronologists at the community-driven and NSF-supported EarthTime Initiative. The science of geochronology is computationally intensive because large volumes of raw data produced by mass spectrometers have to be aggregated and reduced using statistical techniques that produce precise geologic dates. And so you see here the goal, one of the main goals of EarthTime is to calibrate Earth history and develop the geochronological techniques necessary to produce these high precision dates. And it requires robust software for data reduction, analysis, and archiving to support both science and education. So the scientists I met with in 2006 recognized that they were dependent on software over which they had little control, in addition to no free and easy access to the source code. This software ranged from proprietary products provided as part of mass spectrometer operating systems to customized and sometimes proprietary Excel spreadsheets to MATLAB routines that were shared by the community. These specialized applications were not always developed with rigorous processes and testing, yet were trusted by users and based on reputation and history. And furthermore, the scientists did not always have the time, inclination, or training to develop new software or to modify existing software to keep up with the new and evolving statistical approaches to data acquisition and reduction. And so they approached me about collaborating with them and gave me some additional requirements that they were pondering. I must say that one of my collaborators, Noah McLean, is present here in this webinar. So shout out to him. He's at the University of Kansas now, just starting. These requirements included that the software, the applications be open source, and that they provide for real-time interactive data reduction and uncertainty propagation. Secondly, that there would be extensible plug-and-play models of parameters and other inputs into the system. That the software would provide graphical and statistical tools, interactive visual, graphical, and statistical tools. Produce publication-ready artifacts in the form of PDFs and vector graphics. Automatically capture metadata, and we'll talk about this in a moment a little bit more. And finally, produce a standardized and extensible record for transport to and from archival databases. So they, in approaching me, were taking a step across this software chasm, which has been formally identified by a researcher, Diane Kelly, I'm quoting here, who's been looking into this for a while. And basically, this chasm is an artifact resulting from the fact that software engineering as a discipline has pretty insistently wanted to make domain-independent software, and the scientific computing community obviously needs domain-specific solutions. And so this chasm is served to isolate the scientific computing community from advances in software engineering, for example. It's not 100% or anything, but this is a noted phenomenon. And then other people, including Wilson, have maintained that these black boxes or scientific computing devices need to also be vetted and reviewed, peer-reviewed, and with publication alongside the science that they support. That's a goal. And so this is what we mean when we're talking about the software chasm. So as a result of this request to collaborate, I said yes, and I created at the College of Charleston CERTLS.org, which is this Cyber Infrastructure Research and Development Lab for the Earth Sciences, and got NSF funding to support it, which is in place today. And the main goal here is to explore collaborative domain-specific software engineering research in order to produce tools that advance science. That's sort of the mission. But we, in fact, have done that for this uranium-lead geochronology. So part of the process that we learned was how to collaborate, right? We have two disparate domains, software engineering in geochemistry. And even though we've been doing this for 20 years, it seems like we still have miscommunications every once in a while. And it was important, though, to support all the people involved, that we would develop parts of a common language, and in particular, something that's known as a data dictionary, where we literally identify all of the terms that are used in all of the mathematics in the software and in the geology, and give them names and definitions to make sure that we use those exact names in both the software as variable names and in publications when we're talking about things, so that there's always this common entity. Other parts of a common language include visualizations, which are always aid in discussions among domains, disparate domains. Process maps, which is specialized kind of visualizations that allow us, for example, flowcharts or whatever, to see how processes evolve and move. And finally, the notion of prototypes, which are throwaway models of solutions that really help the discussion between software engineers and geochemists in determining whether we're making progress in developing useful software tools. And so with this common language, then we can move to actually doing domain-driven software engineering with meaningful requirements analysis and specification, prototypes, testing, and an architecture with documentation that's meaningful to both domains. So we've spent quite a few years doing this, and the big picture of the architecture is this image here, which you may have seen before. At the center of it is the sample, which is the rock sample from the field. And key to this architecture is that it represents a sort of cradle to grave and back automation, right? The data from the sample is processed by the software, managed by the software, analyzed, and then the results are archived and then can be retrieved from the archive. So this begins by having the sample registered at CSAR and giving it an IGSN, which is an international geosample number, which is a unique number and maintained by the CSAR database, which is called the System for Earth Sample Registration, and it's part of IEDA, which is the Integrated Earth Data Applications at Lamont. And in addition, obviously, to getting the IGSN, metadata is supplied to the CSAR database as well, so that there's a one-stop shop to get metadata about any given sample based on its IGSN. And then, of course, the sample itself is processed and put into the mass spectrometer for measurement. At the software level, the UPB Redux, which is the main artifact of this collaboration, is software that plays a number of roles. It manages the data reduction process and all the way through to the archiving, what I've been talking about. It provides for the live workflow that was one of the requirements of EarthTime. That is, that during the mass spectrometer run, we can literally monitor the data and watch the analysis advance, and provide statistical filtering, analysis, the publication-ready artifacts that we were talking about in terms of PDFs and vector graphics, and then it provides for what we call one-click archiving to Geochron. And Geochron is part of EarthChem, which is part of IEDA, and Geochron is a database that stores a lot of geochronology and thermochronology data of many types. Redux has the facility that the analyst, the user, can at any time push a button and archive the state of their analysis to Geochron as a private document, and then retrieve it from any other device using Redux and continue with their analysis from another location if they wanted. Or this is just a storage mechanism. And then when they're done and ready to publish, they can obviously archive their results at Geochron automatically as well, and eventually choose to make them public through either the Geochron website or through the use of the Redux archiving, the UPB Redux archiving mechanism. So in this way, we're supporting, and in fact, the scientists at EarthTime sort of presaged the demand by NSF that we have support archiving of data by making it now a one-click process. It's very, very sophisticated. Now, there's an interesting, what should I say, development that happened here was we provided what we called something called compilation mode, a way to look at more than one sample at a time after it had been analyzed. And it turned out that this has become a very popular and powerful aspect of this software, and I'm going to show you a little example of how this works. Doug Walker, who's Noah McLean's colleague at the University of Kansas, kindly used Redux for me and provided the slides of the following slides so that I didn't have to demo anything live here. So in compilation mode, in this example, we're going to compile two samples, one a volcanic rock and one a related pluton. And this screenshot just shows from UPB Redux how one might go about accessing stored results at Geochron for importing into UPB Redux in this compilation mode. And in fact, this is where Doug Walker typed in his two IGSNs that represent the CSAR information, and so the metadata is automatically available to UPB Redux via these numbers, and then the actual artifacts, that is the stored data and analysis results, are retrieved from the geochron.org database, which I said earlier is part of AIDA and EarthChem. So using this screen, he's able to type them in, and then basically instantaneously they both appear inside of UPB Redux. And in this case, he selected two, a volcanic and Pluton, that have similar ages. And so in this compiled Concordia plot, you see them both, one in pinkish and one in greenish. This is from the Sierra Jurassic. And on the left here, you can see that there's a zircon, and then where he has aliquot name is this Pluton. Then you can look at each of these, so you can perform analysis on these jointly, or you can view them individually, look at weighted means. If they were originally archived with weighted means, they appear here, and you can add additional weighted means and play with this data set as if it were your own. So this is very powerful. And then in the second shot is the related Pluton. So UPB Redux in this compilation mode allows you to bring together any number of analyses stored in Geochron and view them and analyze them together in UPB Redux.
Jim, this is your 3-minute warning.
Okay. So, my thoughts. Describing a first-of-its-kind collaboration that's been going on for years among software engineers at the College of Charleston and geochronologists at MIT and the University of Kansas and University of Arizona. And we've made some great progress. We have a working tool that people are using, that people are publishing results with. And I wanted to, as closing thoughts, say that it's important that we remember that EarthCube must serve scientists and science, and that, again, plugging this governance phase, demonstration governance, in order for that to happen, we have to join up and participate. I also want to plug in this, the notion of collaborative software and cyber infrastructure engineering as being a sort of a critical new way to approach things here. We have or earth scientists and computer scientists need to come together as much as they can and get support from their institutions for collaborative work in terms of not being siloed but being integrative. Third, we need to think about how we're going to get long-term support for open source software products. I don't want to be worrying about this stuff forever, neither do other people that are writing software. We need to really explore and have hard discussions with NSF and others about how we're going to provide long-term support. We actually have a test project going on now. Some of you might have heard of trying to replace Isoplot with something called Topsoil as a community effort through GitHub. And if you want to know more about that, you can email me. And then finally, the whole point of this automation is less tedium and more science, right? So by having all of the processes open source, people can see what's going on and understand what's going on, but the automation allows them to do more in a shorter time. The software collects the metadata and provides it automatically, right? It's not have to be typed in. It doesn't become an additional chore to talk about collecting metadata and storing it in an archive. So all of these things are good, and I think there are things that we need to think about and moving forward. So I'm going to open the floor to questions here. This is a shot of our Randolph Hall, which was the first building of the College of Charleston, dating from the 1770s.
Jim, thank you very much for that talk.
You're welcome.
Okay. So the first question here is, what are the biggest social challenges in maintaining your software suites and gaining more users?
So change is hard, right? And we basically, the way we gain more users now, and the user base is growing, is by word of mouth and word of science, so to speak. People use it at MIT, or they use it at Kansas, or they use it at Arizona, and tell other people, and they start to use it. So it's a slow growth process, and we, however, have been successful enough to have been asked to extend from pure uranium-lead TIMS analyses to laser ablation analyses, and finally now next year to U-series analyses. So people see the value in this, but it's much more slow going than we ever imagined in terms of getting buy-in.
Okay.
So hopefully that answers that question.
Yes. And here we have a question. Do you have a citation list for publications that have used the compilation mode in UPB Redux?
That's a great idea. I do not, but I keep getting emails from Google Scholar and these various other outfits about citations of our papers, and we have a couple of papers that you can find at the CERTLS.org website, authored by myself and Noah McLean, who I mentioned earlier is present, and Sam Bowring at MIT, that lay out the basics, the mathematical basics and the software basics of this cyber infrastructure. So so the answer is no. That's a great idea, but you can find out incidentally by checking out references to our papers on one of these reference engines that are online.
All right. The next one is, we're asking, could you comment on your views of efforts by groups like GitHub, Mozilla Science, and Figshare in the area of code as research output? I'm not
familiar with that exact notion. I do have a related issue, though, which is that at the College of Charleston and other institutions, the product of our work, right, software itself, is not considered something that counts at the top level for TMP, tenure and promotion, right? Even though NSF has changed the language in their proposals to include publications and products, this particular product of software, it seems to still have a hard time getting any traction, even though it's used to produce science that's published in Nature and Science, et cetera, right? And if we had built a Mars rover, we would certainly get the credit for it, I think. So this is a fight that has to be, is ongoing, and I believe from the terminology you're using, it might be related to what you're suggesting. But code is sort of a misunderstanding that code itself is meaningful, right? So the code, a software product is much more than just the code. It involves all kinds of other ancillary documents like, the documentation, the configuration files, the testing files, you name it, the user manual. All of these things are part of a mature, maintainable software. And so the notion that code itself is valuable is probably not worth pursuing, in my judgment.
Okay. So here's another one. What's an example of an interesting and challenging problem you've had on the computing methods and algorithms side of this project?
Well, Noah McLean, partway through the process, decided that we were going to do the uncertainty propagation using using matrices, and so we have some pretty complex matrix manipulations, and the challenge was to be able to perform these matrix manipulations on the fly in a way while the interactive visualizations were happening, and without really showing the user that anything was sluggish. So we put a good bit of time and effort into making those manipulations as fast as we could and finding good libraries, open source libraries to assist in it. But getting the math to fire as fast as the user could interact with the visualization was initially a challenge that we've solved.
Okay. Next question is, I'm not a geochronologist, but I've heard that recalibration of samples and calculation of their ages is an issue in the community. Does your software address any of that issue?
I'm not going there. I don't really, that seems like a loaded question, and I'm not quite sure what to say. So what does recalibration mean? We do have a mode that we call sensitivity analysis, and that is where there is a slider for every input into the mathematics and for its uncertainty, and the user can slide the sliders for all of the values and play around to see how sensitive the data set is to variations in these input parameters. But the software is designed so that none of these changes stick. There's no way you can make them stick. So that might be considered recalibration if you could make them stick, but in no way can you make them stick. So Noah may have another answer here if he wants to chime in.
Sure, I could chime in just briefly. Can everybody hear me?
Yes, go ahead.
Hi. Yeah, that's an excellent question. And one of the things that Redux does is it makes sure that you're able to change any parameter that ever gets input. And for instance, the decay constants, which are a subject of constant revision, are one of those parameters. So for any data set that you have in Redux, you can go in and update the decay constant, and that effect percolates all the way down through all of the dates. So absolutely, you can use Redux to recalibrate dates.
Great, thank you. All right, we're approaching the end of the hour, and we have one last question here, which is, do you have any needs from the user community that the C4P effort can help you gather? There you are. Okay.
Yeah. So I'm not quite sure how to answer that. I would say, all input is valuable, and suggestions are valuable. We're looking for collaborative efforts, going both ways, obviously. So the user community of UPB, is the question about the user community of UPB Redux or C4P?
The question says C4P, but so I guess it's coming from the viewpoint that we can reach these people easily. Is there anything that we could gather, any information we could gather that would help you?
Noah, any ideas? He's gone. I'm not quite sure how to answer that question.
That is a fair answer. Okay, so thank you very much to both of our speakers today and for the discussion we've had. This webinar will be archived on the C4P website and on the YouTube channel. And in 2 weeks, we'll go back to our regular Tuesday webinar time. So thank you, everyone, especially to the speakers, and we'll see you next time.